Hello everyone, in this lesson we are taking a look at section 5.1, variation function. So our objectives will be to solve problems involving direct, inverse, joint, and combined variation. So we do have some vocabulary you'll see coming up in the lesson, including direct variation, constant of variation, joint variation, inverse variation, and combined variation. Alright, so let's get started here. Starting off, we have that direct variation is a special type of linear function. And we know that linear functions are our equations that are most often written in the form y equals mx plus b. A direct variation is a relationship between two variables x and y that can be written in this form, y equals kx. And that is special, and it only works when k is not equal to 0. If it was equal to 0, it would just be y equals 0 times x, which then is just y equals 0, because 0 times anything is 0. So again, our form for direct variation, and I'm going to highlight this, is y equals k times x. And again, k can never be 0. It can be any number besides that. In this relationship, we call that letter k the constant of variation. So it's constant because once we know k, it will never change. For this equation, y equals kx, we would read that as y varies directly as x. So again, the way we would say that in words, y varies directly as x. So whatever comes first, that letter y varies directly. That means it'll have is equal to k times whatever comes next. And in this case, that was the letter x. So again, it varies directly as x. This form will look a lot like y equals kx. Y equals kx will look a lot like y equals mx plus b, but the b value is 0, and k is the slope. So we can notice here, scrolling down, because b is equal to 0 in this linear equation, the graph of direct variation always will pass through the origin. So if we took some equations, y equals 3x, for example, y equals negative 1/5 x, y equals, let's put a square root in there, square root of 7x. All of these fit y equals kx with different k values. All of them have a b value of 0. And if I graph all of these, we'll see them cross through the origin. So for example, you don't need to graph these, it's just a little visual. If I graph y equals 3x, we notice it crosses through the origin. If we graph, what was the second one I said there? Negative 1/5 x. All right, we'll put that in. Negative 1/5 x. Oops, careful where x goes next to it. That goes through the origin. Or even I just made up one with the square root of 7 with the x after it. All of those, you notice, cross through the origin. So every direct variation will be linear, a straight line, going through the origin, and depending on k, that will change its slope. So we're going to look at some word problems as well as graphing for this type. So example 1 tells us that y varies directly as x. That's our key setup. We have to know what kind of variation we're doing. And it says that y is equal to 27 when x is equal to 6. So we're going to write and graph the direct variation function, but we have some steps. So step 1 is find the k value. Whenever we see direct variation, the first letter varies directly as the second. In this case, we'll say y equals k times x. We will now take what we know for x and y and sub it in, and we'll solve for k, because k will never change. So y, 27, equals k times x, which is k times 6. To solve that for x, well, since it's k, solve that for k, since it's k times 6, we will divide both sides by 6. So k is equal to 27 over 6, but let's grab our calculator, and we're going to just go back. I actually have a calculator page back there at the end. So 27 divided by 6 reduces to 9 over 2, or if you want to make it 4.5, you could, but it's better off usually to leave it as a fraction so that it's more exact. So my k value is 9 over 2, again, or in this case it is 4.5, because that would be a terminating decimal, which means it stops. I didn't have to round that. So again, it is equal to 4.5 as well. Okay, well, we now have that value of k. Let's now write our direct variation equation. The pattern again was y equals kx, and we now know k. So my equation is y equals 9 over 2 times x. And you also in this one could write 4.5x. Well, now I want to graph what that looks like. Okay, well, let's get our calculator, and I'm going to add a graph page here. And on my graph page, I'm going to graph Again, I'll just do it as the fraction 9 over 2, and I'm going to make sure I put the x next to it, not in the denominator. Alright, well, how will we graph that? Let's pull up a table, Control T, and we'll get some x values. We're going to do some positives and some negatives. Again, I'm not going to do 313.5 because that's not going to fit on the grid I gave you. So we can graph 2, 9, 1, 4.5. We can graph 0, 0, which should always cross 0, 0 for direct variation. 1, negative 4.5, and 2, negative 9. Again, that kind of stops where we're able to graph. So I'm going to just take a little snipping tool here just to copy these over. If you want to write them on your paper, if that would help you, you can do so. And let's go ahead and plot, excuse me, wrong button there. Let's go ahead and plot those points. That was very large. Okay, there we go. Plot those points, and we'll draw this in a nice straight line. So negative 2, negative 9 will be down here. Negative 1, 2, 3, 4, 5, 0, 0, 1, 4.5, 1, 2, 3, 4.5, and 2, 9. I'm going to cheat and go ahead and use that arrow tool that I have here to draw in my lines. And we're going to draw in a nice straight line. It does continue forever, so I'll just go ahead and emphasize on the endpoints here. We do want to put arrows on both of those endpoints. I already had one up there. And that is my function for direct variation. Now, we also can use this in a word problem. So, for our direct variation, let's read our setup and see how we would solve this. The cost of an item in euros E, so there's my variable, varies directly as the cost of the item in dollars D. E is equal to 3.85 euros when D, the dollar amount, is equal to $5. So write the model that represents this situation. Well, first thing I notice is it says varies directly. So our pattern is y equals kx, but that's if we're using the letters x and y. We're using euros E, so they vary directly. So E equals k, because k is always that constant, and they vary directly with dollars D, so that's going to replace the letter x. That is my setup, but we're not quite done, because I have to find the value of k. So we're going to say, okay, my euro value, my E value is 3.85, and that happened when the value for dollars was 5.00. You really could just write 5 in there if you wanted. And that will help us solve for k. Well, it's k times that number, so we'll divide both sides by 5. And I'm going to go grab my calculator to see what k is equal to. So on my calculator, we'll take the calculator page. I'll just pull up my scratch pad. 3.85 divided by 5.00. Again, that 5.00 is kind of redundant. But we get that a k value here is 0.77. Okay, well, we're not going to have a fraction, so we'll just use the decimal with the decimals given. And now we can write our model. The pattern we started with was k equals, highlighted, or excuse me, E equals k times D. So now our model is E equals 0.77 times D. We want like a follow-up equation to be possible, so we need to have that equation with the variables in the correct spots filled in. We now can use that for part B. Find the dollar amount when the euro amount is 10 euros. Okay, so we're going to plug in 10 for E. So 10, you can write 10.00 if you'd like, or just 10 would be fine in this case, is equal to 0.77 times the dollar amount. To solve for the dollar amount, we'll divide both sides by 0.77. And we'll go to our calculator to find out how many dollars this would be. And we'll round appropriately because it is dollars. It is American money. So we will pull up this. I'm going to do 10. And if you want to say 0.00, you can. Divided by 0.77. And that gives us 12.987. But we know that if we write that down, we'll go ahead and write that and then we'll round it. American money only has 2 decimals, so this 7 is going to bump that 8 up to a 9. So my answer for dollars would be $12.99. Okay, so there's our example of some direct variation. But as you saw, we have lots of types of variation to talk about, so let's move on to the next one, which is called joint variation. Joint variation is a relationship among 3 or more variables, and it's written in the form of y equals k times x times z. So it's similar to direct. Direct, I'm going to highlight here, which is y equals kx. Joint variation just brings a different letter or an additional letter multiplied at the end. So it is y equals k times x times an additional letter c. Again, k is the constant of variation. It's the value that once you find it, it will not change. It stays the same in here. we're not going to graph these, we'll just use them in word problems. For the equation y equals kxc, we read that as y varies, the first letter y in this case, varies jointly as x and z. So notice you never say the letter k when you are reading these. The joint variation or direct variation implies that you have that constant of variation in there. So example 3, we're going to try it with a word problem. Again, I'm going to keep that pattern right at the top so we can see it, and I'll drag this up just a little bit to help us out. It says that the volume V of a cone varies jointly, keyword here, as the area of the base, capital B, and the height h. Okay, so before I even read some numbers to plug in, let's get a model started. Well, since I see the word joint variation, I would start that with y equals k times x times z. And again, x, y, z are just some variables in the setup of the generic equation. In this one, v varies jointly. So we'll say capital V equals k times what comes next. Again, the varies jointly is the part that's telling you equals k times what's about to come. Our next letters, it varies jointly as the base b, so capital B, and the height h, lowercase h. That is my setup before I plug in the numbers that I know. The volume of the cone is 12 pi, feet cubed is just my unit. When the base is 9 pi, again, feet squared is just my unit. And the height is 4 feet, and again, feet is just the unit I would use here. So to plug in volume, I'm going to highlight so that they match. The volume here was 12 pi, so we're going to plug that in for V. Let's start doing that down below. So 12 pi is equal to, we're going to have to solve for k. We don't know it, so let's leave it as k. The base B, the area of the base, was 9 pi feet squared, so we're going to plug that in for our base, 9 pi. And my height was 4 feet, and again, we're not going to put the units in, we'll just put the 4 in, and we'll plug in 4 here. Alright, I'm going to scoot all that over just so I have a little bit more room to work as I'm solving it. Pardon me about that. Let's go back, line that all up. And I'm hopefully going to try to group this. Let's lock it so it doesn't move again. And I'm going to bring all of this work, at least, a little bit over for us to work on. Okay, so in order to solve here, how would I solve for k? Well, I would probably take a second and clean up this right side of the equation. So we're still going to have 12 pi. It's going to equal k times something. But if I multiply 9 pi times 4, that's 36 with the pi. We want to leave the pi in there because that's exact to leave it until we get our final answer. To solve for k, we're going to have to divide both sides. To get k alone, we'll divide by 36 pi and 36 pi. Notice that there's a pi in the numerator and a pi in the denominator, so those will divide out. So to solve for our value of k, we're just going to take 12 divided by 36. So I'll grab my calculator. We'll take 12 divided by 36, and as a fraction, that's 1/3. Again, as a decimal, if I grab that, that one is not truncated. By that, I mean it's not terminating. It doesn't stop. I don't think truncating is a word. I think it's not terminating. That's the word I wanted to use. So it's 0.3 repeating. So using 1/3 is much more exact in this problem. So we'll say our k value is 1/3. Well, what is our model now? Well, our model is going to be where we started, but we now know this value of k. So V equals 1/3 times the area of the base times height. And that's the model we need before we can move on to any follow-up questions. Okay, we're going to take that and we're going to apply it to part B. In part B, it says to find the base of the cone. Well, again, the base was B, so we're looking for what B is. If the volume, V, is 24 pi, again, its unit is feet cubed, and the height is 9 feet, I'll just write that over here, height is 9 feet. So taking our equation from up above, I'll rewrite it right here. V is equal to 1/3 times capital B times H. We're going to sub in V, 24 pi, not the feet cubed, that's just our unit, is equal to 1/3 times the base. Well, I don't know B. And the height is 9, again, its unit is feet. So let's solve this for B, and then we'll put units after we have it. We have 24 pi on this side. If I multiply, I'm going to multiply 1/3 and 9. So it's going to be B times what number? Well, again, if you want to grab your calculator to help you out just to verify, but 1/3 times 9 is just 3. So that is going to be 3 times our B value there. And now to solve for B, we'll divide by 3 and divide by 3. Alright, so we have b alone. We can divide by hand. 3 goes into 24 8 times. Again, if you want to check that on your calculator, I would just do 24 divided by 3. That is 8. So we have an exact answer that is 8 pi. So my base, area of my base, is 8 pi. Or if you do that as a decimal, we can do that as well. 8 times pi. Pi key is down here by the h. That is 25.1327. Or 25.1327. But we do need some units. So what was the area of the base measured in? Well, I'm looking for it in part B, so I'm going to have to travel back up to part A to see where they gave me a measurement of base. Well, the base was given right over here, and it was given as 9 pi, and its units were feet squared. So my answer down here will be 8 pi feet squared, or as a decimal, we'll say 1327 feet squared. And again, that would be my final answer. On a test or a quiz, we would let you know how much you need to round. But again, in this case, 8 pi is exact as well. So that's joint variation, just like direct but an extra variable. We now have a third type, and this third type, again, from that vocab we knew was coming our way, it describes a situation in which one quantity increases as the other decreases. Oh, and speaking of that, I think I actually missed, let's go back for a second. You need to fill in, I forgot to scroll down, way back on the front page here under your graph, you're probably like, hey, she never said this. Let's go back and fill that in. For direct variation, as one quantity goes up, the other one goes up. So take a look at this. As my x's got larger in my table, my y's got larger in my table. And likewise, as one quantity goes down, the other goes down. So as x got smaller, then the y's got smaller. So direct variation, because it's a line, they do the same thing. One gets bigger, the other gets bigger. One gets smaller, the other gets smaller. But in inverse, which is what we're about to talk about now, well, that's going to do the opposite. One thing will go up while the other goes down. One value will increase as the other is going to decrease. And this type is called inverse variation. So inverse variation, kind of like almost like opposites, doing different things. It's a relationship between two variables, x and y. Again, that's what we're calling them in this. That can be written in the form of y equals k divided by x. And again, k cannot be 0. Because if that was the case, well, then you'd have 0 over x, and again, that would just always be y equals 0. So we're going to rule out that case. So again, the form of inverse, whenever we see inverse, our setup for that will be k divided by x. All right. When we take a look at that equation, k divided by x, the way that we would read that in words, again, is y, whatever the first variable is that's given, varies inversely as x, whichever the second variable is given. What will you never read out loud? You'll never read out this k. The varies inversely is what tells you to take, okay, equals k divided by what comes next. All right, so that's your setup for that. So for example 4, given that y varies inversely as x, so the first letter we'll have is y, it varies inversely, k divided by what comes next as x. We want to find the equation for this, find the graph, what it looks like, and we have to do that by finding k first. So y varies inversely is our pattern y equals k over x. We are going to plug in what we know, so y is equal to 4 when our x value is equal to 5. To solve for k, we'll multiply by 5, multiply by 5, so it looks like our k value in this case is 20. Okay, what would our equation be then? Well, my pattern was y equals k over x, so our equation is y equals 20 divided by x. Let's go ahead and graph that on our calculator, and then we'll plot those points here. So I'm going to open up a graph. I'm going to get a fraction to start off, 20 in the numerator, x in the denominator. Notice how different an inverse function looks. You have two pieces of this, so we are going to need to graph both parts of that. And if I pull up my table Control T, let's talk about what numbers to do. Well, notice at 0 it's undefined, so at 0 you never can plot that. If I try to plot 120, well, that's going to be too big. So 210, that would be the first point I'd plot, and those are the ones up here on the right side. And I'm going to arrow down. So I would probably not plot 3, 6.6 repeating. Let's do the ones that are easy to do. So 210 looks good, 4, 5 looks good, 5, 4 looks good, and then I'd probably skip the one at 6, skip the one at 7, maybe pick up 8, and then I would probably for sure do 10 too. So we're kind of doing those pairs that kind of match up. So again, if I was going to do these, I would plot 210, and I'll even make a little chart for you of what I'm saying I would probably graph. So let's just do, we'll just do an XY table here. So I probably, for this part, would plot 210. I would have plotted 4, 5, and I'll go back to my calculator in a second. I would plot 4, 5, also 5, 4, and make that a little bit straighter for us. I would plot 5, 4, and then I probably wouldn't go grab another one until 10, 2, if I'm looking at my graph. If you want to do like 8 and 2.5, you can, but you should do as far as you could go. So I can't do, 10, 2. I can do that, but then all these other ones, look how small they get. So 10, 2, 21 is too far out. So 10, 2 is where I would start. So let's go do that part. We're going to graph those, and then we're going to do the same thing with the negative. So I'm going to plot 210. I'm going to plot 4, 5. 1, 2, 3, 4, 5. I'm going to plot 4, 5, 4, and then 10, 2. All right, and I'm going to draw that in with a nice curve. Kind of hard for me to do on this, with some arrows. But we need to get this other side as well. The nice side is it's just a reflection. So when we go on our calculator to go plot some points, if we start going into the negatives, again, we're not going to be able to use 0. We're not going to use -1, -20, but I can use -2, -10. I can use -4, -5, -5, -4, and then I probably wouldn't do another one until -10, -2. So I'll just take those same numbers I have, but they're all just the opposite sign. So we always want to plot both parts, positive and negatives. So I'm doing -2, -10, -4, -5, -5, -4, and -10, -2. Again, the more you plot, the better the shape of your graph is and the more accurate it is. So we want to do as many as we can. So I'm just counting so I'm accurate, plotting those in and drawing that in with a nice curve. Again, it's no longer a straight line. And that is our function, our inverse function. Okay, so you're looking for the ones that are whole numbers, looking for the ones that fit on your graph, and doing as many of those as you can. Okay, let's now take a look at how to do inverse variation in a word problem. So for this, we have the time t, there's a variable we'll need, needed to complete a certain race varies inversely, again, that's telling you what formula or pattern we're going to use, as the runner's average speed s. So before I even keep reading, inverse variation. The general pattern was y equals k divided by x. But my first letter was t, so t equals k divided by, my next variable was s. This is the pattern that we're going to use to keep working in our problem. Again, I'm going to go ahead and lock this part in place so it's not going to move, and I'm going to drag over this formula we just wrote. Okay, now let's keep reading. It says in this problem that a runner with an average speed, so the speed, the value of s, is 8.82 miles per hour. So s is equal to 8.82. The units are miles per hour. And this runner is going to complete the race in 2.97 hours. Well, that's my time. 2.97, again, h is my hour, which is my unit. So let's plug these in. My value for t will be 2.97. We're going to exclude the unit. And my value for s will be 8.82, and we'll plug that in for s. That blue is going to be hard to see there. So we will set this up as 2.97 is equal to k divided by 8.82. And again, we have to start by solving k. So we'll multiply by 8.82 on the right and by 8.82 on the left. So let's grab our calculator. We're going to multiply on Scratchpad, sure, 8.82 multiplied by 2.97, and that gives me 26.1954. Again, a lot of decimals, but let's keep them to be exact. So again, our k value in this case will be, I already forgot, let me go back and look, 26.1954. 26.1954. 26.1954. Usually we'll probably round this to 2 spots, but for this we'll just keep it exact. We'll talk about in class how far you should round it. Alright, t is equal to, what's our model? 26.1954, that's my k value, divided by s. Again, I went back to this pattern. I just plugged in k and left t and s as they were. So I'm going to box it so we know that that's our formula we're going to use to go forward. That is our model. Our model is what you get once you find k and plug it in. Okay, and using that now, in part B, what is the average speed of a runner? So the speed, what is s, So a runner who completes the race in 3.5 hours. So the time is 3.5, my unit is hours. So my formula is T equals 26.1954 divided by S. So to plug this in and solve, we'll say 3.5, again, we're excluding the unit there, is equal to 26.1954 divided by S. Well, how are we going to solve that for S? It's in the denominator. So we'll start by multiplying by S on the right and multiplying by S on the left. So 3.5 times S, put that in any order, is equal to 26.1954. And we'll divide both sides by 3.5 to solve for it. And we're going to go grab our calculator. This will tell us what S is equal to. We're going to definitely have a decimal in this one. So in our calculator, 26.1954 divided by 3.5. That gives me a value of 7.4844. 7.4844. So 7.4844. Well, I need some units here. And if I go back, where else was speed given? Way up in the beginning, and its unit was in miles per hour. So my unit here will be miles per hour. Again, we'll probably give you some rounding direction. So perhaps we'll round to like 2 decimals. So that might be like 7.48 miles per hour. But just ask how much we'd like you to round. Okay, but the most exact we can have based on the work we did would be that original one, 7.4844 miles per hour. All right, so there's a word problem with inverse. Now, there is one other type. Before we do that, I just want to make sure we have these two patterns down. Anytime it's direct, that's y equals k times x. So indirect, so we'll talk about this part actually here in a second. So let me just hide that for a second. So it's y equals k times x. So really, when you're solving for k, what's your process? Well, to get k alone, you're dividing by x and dividing by x. So that's what the second formula is. Anytime you're looking for k, it's just really y over x. That's like how you undo direct variation. Inverse, we know is y equals k over x. Well, what's my process to solve for k every time? I multiply by x to get it out of the denominator, multiply by x to get it out of the denominator. So that's why an alternative form, if you're solving for k, is just to take x and multiply it by y. So that's still an inverse form. It's just the form solving for k. Just like this one on the left is still a direct form. It's just the form solving for k. So where your variables are does matter. Not that we would ask you to solve this, but just for reference, I'll just kind of put, if it was a joint variation, we know that's y equals k times x times e again. Good to remember that that was the other form we talked about. If you were going to solve for k in that one, I'm going to write it over here, k would equal y divided by x times e. So give both of those to the other side. Okay, so on your notes now, pick up. It's an indirect variation. When you divide y by x, you get a constant. That's what it's saying right here. That's how you find the constant, y divided by x. That's that process. In inverse, when you're solving for k, well then you're multiplying x by y, because that's what you would do to undo the inverse variation, to solve that constant you're looking for. So if we're doing that, we can use now some equations just to say if the equation is given, is it direct or inverse? And also from a table of values, is it direct or inverse, or neither? So for example 6, I just want to identify just from the way it looks, is this going to be direct, inverse, or neither? Well, in number 1, y is solved for, so we're going to say, does this fit y equals k over x, or excuse me, k times x, or k divided by x? Well, this has a number 4, and it is divided by x, so this one is going to be inverse variation. And not that it's asking us for it, but it might be helpful just to say, you know what, the k value here would be 4. I do recognize it's inverse. In number 2, is this inverse, direct, or neither? Well, this is in the form where the number is being solved for. We have 4 solved for this. So what I might do is I might say, you know what, I think it's probably easier. Let's move x back over, and this is equivalent to y equals 4x. Well, that is a number times x, so this is direct. And in this one, this also indeed has a k value of 4. In our third one, is that inverse, direct, inverse, or neither? Well, to get y alone, I would divide by 3. That was the form that was solving for k. So we would say, okay, well, y is equal to 3 over x, if I wanted to see an equivalent. So that is going to be our inverse form over here. I'm highlighting in blue. And our k value is 3. I kind of used my line there. So it is inverse, and our k value is 3. And then the last one for number 4, y is already solved for, so we're either hoping for this to be y equals k times a number, or y equals k times x, or k divided by x. Well, I have this extra minus 4. Neither one of these have anything added or subtracted after them, so this last one will be neither direct nor inverse. It does not fit either of those. But neither of these patterns have anything added or subtracted at the end. It is just k, and then the k is either times x or divided by x. Or in joint, you'd have 2 more things multiplied by it, by the k. All right, let's try example 7. Again, we are going to now take a table of values and decide, does this represent direct variation? Well, direct pattern, we're using x's and y's here, y equals kx. Inverse, y equals k divided by x, or neither. If it does fit one of these, we'll write its equation. If it's neither, we'll say y. Okay, that's the general pattern, but in all of these we know x and y. So really, if we're finding direct, we're hoping that every time we solve for k, we're getting the same y over x for every ordered pair. If it's inverse, every time we solve for k, we're hoping that, I'll do it under here, when you solve for k, every x times y is the same. Again, that's just this other half of the table. To solve for k in direct, it's really a division. To solve for k in inverse, it's really a multiplication. So we're just going to see which pattern is either these ordered pairs fit. So in A, if I wanted to check if this was a direct variation function, every ordered pair, every xy, would need to fit the form y equals kx. But I don't want to have to plug in x and y and divide by x every time to see if I get the same k. So I'll just use the alternative form where I'll say I'm just going to check if every y divided by x is the same. And then if every k is the same, we're good to go. So to check if it's direct, we're going to start off with y divided by x. So is 8 divided by 6.5, is that the same as 4 divided by 13? Is that the same as 0.5 divided by 104? So we're going to grab our calculators, and we're going to start checking those divisions. So is 8 divided by 6.5? That is 1.23077. Is that the same as 4 divided by 13? Well, that gave me a fraction. Let's go ahead and do it again. But we'll hit Control equal or put a decimal. We're already getting that those are not equivalent. Those are not the same values. So we're going to say, already, that's not equivalent. I'm not even going to check this other one. Well, I take it back. I will. 0.5 divided by 104. Those are not all the same. So this is not direct. So not direct. If I want to check if this is inverse then, and I'm going to go ahead and scoot this down. I know you guys don't really have the ability to do that, but I am going to move this just so I have a little bit more room. If I want to check if it's inverse, well, every time it would be inverse, it's going to fit the form of y equals k over x. Again, but just save myself a step. I'm solving for k every time. Well, that's like multiplying by x, so I'm going to see, is every x times y the same? And if so, that's my k. So is 8 times 6.5, is that the same as 13 times 4? Is that the same as 104 times 0.5? So we're going to grab our calculators. Okay, on my calculator, 8 times 6.5, that's 52. And 13, what order did I put on your paper? Let me make sure I do the same one. 13 times 4, that also is 52, good so far. And 104 times 0.5 is also 52. So all of those do come out to be the same. Yes, these are equivalent, and they are all equal to 52. That means my k value is 52 because every x times y was 52. So this one is indeed an inverse function, and its equation is y equals, now what's my pattern for inverse? It is 52 divided by x. And you can check and see if that makes sense. Just test some numbers. If I take 52 divided by 6.5, do I get 8? You will. 52 divided by 13, do I get 4? I will. And divided by 104, do you get 0.5? Yes, indeed. All right, let's try B. We're going to check if it is direct. And again, I'm going to take a second and move this down just so I have a little more room. Okay, so to check if this one is direct, I'll start off by setting these up and say, okay, if it's direct, well, that pattern would have been y equals kx. But again, I'm going to be solving for k every time. So I want to know if every y divided by x is the same. So is 30 divided by 5, is that equivalent to 48 divided by 8? Is that equivalent to 72 divided by 12? Again, it has to be y over x, y over x, y over x. Well, 30 over 5 is 6. 48 over 8 is 6, 72 over 12 is 6. So those all do match. So my k value is 6. Don't have to check inverse because this one works. So this is direct, and what's my formula? Remember, we started off with y equals kx, so my equation is y equals 6x. So this is direct. Again, my formula is y equals 6x. That's my equation. So to check it, y equals, so is 6 times 5, is that 30? Yes. 6 times 8 is that 48? 6 times 12 is that 72? All yes for those. Let's try C. All right, taking a look if it's direct. I just did that above. We're going to see if every y over x is the same. So is 5 over 3 the same as 14 over 6? Is that the same as 21 over 8? Go to my calculator. So 5 divided by 3, let's put a decimal in so we get a decimal. Is 5 over 3 going to be the same as 14 divided by 6? Already they don't match. If you want to check just for completeness, 21 over 8, those are not the same. Even if 2 out of 3 are the same, still doesn't work. They all have to match. So we would say no, not true, so not direct. Okay, let's see then if it's inverse. If it's inverse, our original pattern is y equals k over x. We're going to be solving for k every time in this when we check, when we scroll just a tad. So times x times x, I'm looking for every x times y to be the same. Well, is 3 times 5, is that the same as 6 times 14? Is that the same as 8 times 21? Well, 3 times 5 I know is 15. Let's see if that's the same as what we get if we go to our calculator. So again, 3 times 5 was 15. We then had 6 times 14. 84 already doesn't match, and 8 times 21 is 168. So those do not match. So this again was equal to, let's put our numbers in for the sake of this one, 84 and 168. That's a no. Those do not match. So this is also not inverse. So this one would be not inverse, not direct. So this one is neither. Again, we're only going to test for those two. We're not going to give you a table and ask you for joint, because for joint, you'd have to have like a z column also because you need an extra variable. All right, that leads us to our last type of variation and our last problem on this. It is combined variation, and as the word indicates, it's going to take some of those we've done and put them in one problem. It will have a relationship that contains both direct and inverse. So quantities that vary directly, so if you see that, they'll appear in the numerator, and quantities that vary inversely will appear in the denominator. So hopefully that kind of makes sense. If it was direct, we're used to saying y equals kx, so like that's like over 1, right? That's in the numerator. Where if we had inverse, we're used to writing that one for an inverse variation as y equals k over x. Notice that that x is in the denominator, excuse me, in the denominator. So k always stays by the equal sign on the top, but do I multiply by it or do I divide by it? Well, it depends if it's direct or inverse. So for example, 8, the volume V, and again, I should also point out, there's not like a general pattern here because it depends on is it direct or inverse and then how you'll build stuff. But whatever the first letter is always still comes first, and you always have it equals k, and then you decide divide or multiply. So the volume V, let's highlight, there's a variable we'll need. It varies inversely as the pressure P, okay? So inverse with P, and directly, that means V again. V is directly varying now, directly with the temperature. I'm going to pause and write my model. It is one model for this setup. So to vary inversely, again, that setup would have been y equals k over x. But in this case, we have V equals k inversely divided by P. That's step 1. But I have to keep building onto this equation. It is now directly varying as t. Well, again, direct was k times something, so we're going to go to where k is, and we're going to multiply it by the letter t. Again, it makes one equation. Most common mistake I see is people write, oh, v equals k over p, and then they write v equals k times t. Well, you're kind of right, but it has to be combined into one model to use. Okay, so we have to put the t in the numerator, the p in the denominator, k is just there once. So let's take that and now plug in our numbers. So what are our values? I'm going to erase this so I have room to work. We know those are not separate. It says that the volume of this, so let me keep reading, a certain gas has a volume of 10 liters, so liters is the unit. a temperature, that was green, of 30 kelvins, and kelvins is your unit, and a pressure of 1.5 atmospheres. And atmospheres is your unit. So let's plug in and solve for K. So V equals, I'm going to do it over here on the left, V equals, so that was 10 equals K times my temperature, that was 300, over my pressure, which is 1.5. Okay, in order to solve, I probably would just go and multiply both sides by 1.5 to start. You could also divide 300 by that, but I don't know, that's just my go-to method. So 1.5 times 10 gives us 15 on that side. Okay, so 15 is equal to K times 300. And then I'm going to divide both sides by 300. And let's see what K is equivalent to. So on my calculator, 15 divided by 300 is 1 over 20. Again, if you did this one as a decimal, you get 0.05, and that is terminating, so you could use that, you wouldn't have to round there. But I'll just leave it as 1 over 20 because that's a nice fraction that's exact. So what is my model? Well, V equals 1 over 20, I'm replacing the K, times T over P. And just leave that fraction up there where K is. That's fine. That's what we'll use for our follow-up. So again, your model is complete once you have a value for K and everything else stays as a variable. We're going to take that now and go to our follow-up question for our last part of our notes. If the gas is compressed to a volume, I need to have something to write with here. Here we go. A volume of 7.5 liters, so V equals 7.5, and is heated, I scrolled over a little tad too much, can't read that number, is heated to 350 kelvins. Again, Kelvin, look at your unit. Kelvin was our temperature, so that means my temperature, my value of T, is 350. Again, I'm not going to put units on here. What will be the new pressure? What is P going to be? Well, we have this equation, our model. V equals 1 over 20 T all divided by P. So we'll plug in what we know. 7.5 for volume is equal to 1 over 20 times my temperature, which is 350, all divided by P. How are we going to solve? I would probably start by multiplying both sides by P. Well, that's just going to give us P times 7.5 equals 1/20th times 350. Let's go to our calculator and figure out what number that is. So 1/20th, or again, if you did a decimal, that would have been 0.05. And we're going to multiply this by our temperature, which again was going to be 350. So we have 35 over 2. Again, that also nicely does give you a nice decimal there, which is 17.5. That might be better to change to 17.5 at this point, but your choice. So 17.5 again, or you could have that number as 35 over 2 at this point. And then we're going to solve for P. So we're going to divide by 7.5, divide by 7.5 to figure out what my pressure is. All right, so 17.5, you can retype or just have your calculator do that for you, divided by 7.5. And we get 2.33333, 2.3 repeating. So exactly it's 2.3 repeating. Probably will have your maybe rounded, like say 2 decimals, so 2.33. And what is my unit for pressure? Well, I have to go way back up to the beginning where they first said pressure. A pressure of 1.5 is measured in atmospheres, so you can abbreviate it as ATM, and that is our unit. Atmosphere is how this is measured. So ATM, or again, you could go here, ATM. Atmospheres is what that is. So that is our unit for our pressure. Okay, that does finish our notes for this lesson. If you have any questions, please let us know.